All right, here we go. So we're going to do continuity, which is a little bit of an application of limits. So continuity is drawing the graph without lifting your pencil. Okay, well, that's like our old definition of continuity. We're going to use the calculus definition of continuity. Okay, so there's three parts to it. And the first part says that there's a point on the graph. All right, so that looks like f of a. Now notice that this is at a specific point. Okay, so f of a exists. All right. The second part is the left side. Okay, that means that the limit as you approach from the left, okay, actually equals the point. There's a point, and the line comes into the point. And then the third part is for the right side. Now, I set it up in a horizontal fashion because it's going to end up with an equation that you just compare. So it says that the point equals the left side equals the right side. Now, some of these things can be the same, right? So you might connect the point in the left, you might connect the point and the right, and you might connect the left and the right. They might be the same thing depending upon the equation. Okay, so over here I'm just going to write 1, the point exists, right? There's a point and I get a number. 2 and 3 kind of come together. This means that the limit, if I say the limit exists, that implies that the left and the right are equal, right? The only way the limit can exist is if the left and the right are equal. And then the conclusion is you compare. You compare the values. If they're all equal, it's continuous. If they're not, that's when you get these different discontinuities. So the conclusion, f of x is or is not continuous. And that's based on how you compare those three values that you have found. Okay. I prefer to do it graphically because it's much easier to see the discontinuity, and then we're going to write the limit statements that correspond to it. So we're going to draw a jump discontinuity. Okay, I'm just going to go in quadrant 1. Okay. I'm just going to label. And I'm going to put an open point here. And a closed point here. All right, so I drew a jump discontinuity. And we're going to write the limit definition of continuity, and we're going to fill in the values and compare and see what it looks like so that when you do it algebraically, you have a picture to connect it back to. Okay, so the first thing I do is the point. All right, now we're going to look at the continuity, continuous at x equals 1, question mark. I mean, obviously I can see the answer is no because it's not, but I do have to have a value in question when I'm looking at this. Okay, so the point, f of 1. is 2. Okay, because I can read the point off of the graph. The second thing I have to do is find the limit from the left. Okay, the limit approaches 1 from the left. Is 1. Okay, the third thing I have to do is the limit from the right. So notice in this particular example, these two pieces are actually from the same line, right? The right and the point come from the same thing. So I could have put them next to each other and just done it once. So now you have to compare. Well, they're not equal, but based on the comparison, you have to envision the picture and figure out what kind of discontinuity it is. So these two are the limit. The left and the right are not equal. So f of x is not continuous because there's a jump at x equals 1. That's why it's not continuous. And it's because I was comparing the limits. I was like, oh, the left and the right aren't the same. That has to be a jump. As we move forward, instead of having a graphical prompt, you're going to have an equation that you look at. Okay, so the next one we're going to do is a point discontinuity. And another word for point is removable. And we're going to answer continuous at x equals 2, question mark. And we're going to draw a picture. And then we're going to do the same thing. And we're going to look at how the 3 statements play out as we look at the continuity of this. 2, 3. Okay, so, I mean, I can look at it and be like, it's not continuous. I have to lift my pencil to draw this, but I want to see what the algebra says. So the first thing I do is I check the point. So f of 2. Well, f of 2 is 1. Okay, there's a point. All right, now I have to see if the line actually comes into the point. So the limit, and sometimes I get a little bit lazy and I just write left and I just look at it. It's fine. From the left is 3. And from the right is also 3. And then I compare them and figure out, right? So if I were to take away the picture, your goal is to try to figure out, can you envision what kind of discontinuity just from the algebraic statement? Okay? So if the left and the right are the same, but the point is somewhere else, okay? So f of x is not continuous because there is a hole. right? Point discontinuity, removable. That's also called a hole because it's a missing point, okay? Because there is a hole, right? The left and the right are equal, but the point is somewhere else. There is a hole at x equals 2. And I think because these two are equal, that's what tells me there's a hole, because the point is somewhere else. Because the point is somewhere else. The limit's there, but the point isn't. Or maybe the point does not exist. What if there's just no point in general? It would still be a hole in the graph. This one just happened to be filled in. But if I do this, it's still a point discontinuity or a removable discontinuity or a hole. So you don't have to have a filled in point. This could be does not exist. It's important that the limits are equal and the point is something else. All right, last one is our infinite discontinuity. There is another word here, non-removable. Okay, so there's my graph. Sometimes we call non-removable is also infinite or vertical asymptote. They say infinite because infinity shows up in the limit statement. All right, here we go. So we're looking for continuity at 4. So we try f of 4 and it doesn't exist. There's no point. Okay. Okay, I try the left. Well, to the left of 4 is positive infinity. And then I try the right. And the right of 4 is negative infinity. And then I compare. Okay, so if I compare these, in this particular case, it's these infinities that are telling you it's a vertical asymptote. So it's not continuous. Because there's a vertical asymptote. How do you know there's a vertical asymptote? Because you already learned that with infinity as the answer to the limit, it's a vertical asymptote. And that came from comparing these two parts right here. Right? Is because the limit was equal to positive or negative infinity. That's what told you it's a vertical asymptote. Okay, so for number 1, is it continuous everywhere? Yes, because it's a polynomial. There's actually a theorem that says polynomials are continuous. It's fine. You just should know that a polynomial is continuous. Okay, so this one is no because there's a vertical asymptote at x equals -2. So we would call this infinite discontinuity. Okay. Now, this one might take me a little bit of work, just a little bit, but I see there is a hole and a vertical asymptote. So there's two reasons that this is not continuous. So no, because there's a hole at x equals 4, so that one is called removable, and because there's a vertical asymptote at -4, and this is non-removable. I guess I could have said infinite or as well. Okay, but there are different vocab words for that. All right, so now we get to number 4. This is where most of your continuity questions show up because it's a piecewise function and you don't know what's there. And this is where the left and the right could possibly be different. So this is where I'm going to use my definition. Point, left, right. Check the point at f of 1. Oh, look. It doesn't actually exist. There's actually no point. So this is does not exist. Notice how 1 is not included in the domain. Okay, so the left comes from the x squared part, which is 1 squared, which is 1. The right comes from this part, which is 1. And then the conclusion comes from comparing them. Turns out the left and the right are equal, but they're not equal to the point. So there's no point, okay? No point, but the left and the right are the same. That's me trying to think of the picture that goes with the limit statement. So the answer is no, because there's a hole at x equals 1. But in this piecewise definition, you have to check each of the places where the function is changing. So now I have to check 3. So I've got to check point, left, and right. Okay, so at 3, the point is 4, right? Because that's where it's included. The left is the x squared minus 2x plus 2. Okay, so 9 minus 6. Thank you. 5. And the right is 4. Okay, so notice that in this particular one, the point and the right side are the same. So obviously, but they're not equal. So let's see. This means that the right side and the point are the same, and the left side is different. It's higher also. So this answer is no, because there's a jump at x equals 3. So when we were drawing the pictures that went with the limit statements, when you're giving your answers, especially on piecewise, you're going to have to figure out whether it's a hole or a jump, because it could be either. Okay, so I'm going to cover up this part for a second. The left and the right are different. right? So you just have to kind of visualize what those numbers are doing. And then how did I know to fill in the point on the right side? Because those are the two things that were the same, right? The point and the right side were the same. That's why I drew it like this. Okay, now, second type of question we're going to do. Given that the function must be continuous, all three parts equal, find the missing value. So I'm going to zoom in here, and I'm going to do 6 and 8, and I'm going to let you guys do 7 and 9. Okay, find K or A so that the function is continuous. That means the point, the left, and the right, they all have to equal. Have to. That's the only way to make this continuous. So the point comes from h of 1. Now, obviously, I'm going to use x equals 1 as the point in question because that's where the piecewise is changing. That's the part that I need to make sure it matches. So h of 1 is 1 plus 1 is 2. I'm going to go a little color coding. The point and the left are the same. So guess what? I'm not going to redo it. I'm just going to leave it there. The point and the left are the same. So now I'm going to move on and I'm going to try the right side. The right side comes from this part. Okay. And it's got to equal 3 plus a. And I'm changing it to a capital so I don't confuse it for a number. Okay. And I'm just going to circle that because that's the equation that I'm comparing. Those two things have to be equal if the function is continuous. So a is -1 because subtract 3 from both sides. So a equals -1. Find a or k so that the function is continuous. Because I set up the continuity definition, all three of those things have to be equal. I'm solving whatever equation resulted from that. I did not rewrite the left because I noted that the left and the point came from the same thing. So I don't need to write it twice. I just showed that they're the same. Okay. Number 8. Oh, man, that's a tricky definition. So let's see. The left and the right and the point. This is why you have to know how to interpret piecewise. Okay, so I have to compare the point, the left, and the right. Based on this piecewise definition, that top part is the left and the right, and the bottom part is the point. So that's where I'm going to set it up. So the point, g of 5, is equal to k. That is the output. Okay. Because this takes a little more than just direct substitution, I'm actually going to do the work here. So the limit as x approaches 5. Oh, okay, because I did get 0 over 0. So I knew there was a hole. And so I'm going to keep evaluating. and then I plug in again, and I get 5 plus 2 over 5 plus 5. And all three of these things has to be equal. Oh, so there wasn't any solving, but K has to be 7 over 10. Okay, I'll finish color coding. The left and the right came from the same thing, which is why I only wrote one limit statement to evaluate it. All right, and then the point came from there. Okay, so I'm going to show you how I would confirm my answer graphically. And I'll do it for both of them. Like this. So I'm going to look at this one right here, and I'm going to type it in, y equals x plus 1. But I'm going to put the domain next to it. X is less than or equal to 1. So it automatically cuts it off. And notice the point is also there, 1, 2. Okay, so now I'm going to type in the next one. Y equals 3 plus ax squared. It's going to make you add a slider for a. And then I'm going to put in the domain next to it. X is greater than 1. Now, as I move a, there's the continuous function where the left and the right are equal. Now, this says a is supposed to be -1, right? You can slide it. Noticing as a changes, it's a jump, it's a jump, it's continuous. So that's how I can check it graphically to make sure you actually have a continuous function resulting when you get that a value. All right, so now I'm going to hide these, okay? And I'm going to try the next one. Okay, so this time I've got y equals x squared minus 3x minus 10. I've got x squared minus 25. And I'm going to put the domain here. X, okay, I'm going to need the keyboard. Can't equal. See if I can find my can't equal signs. I don't know if I can find a can't equals. All right. Well, can't equal 5 is less than 5. And more than 5. I think that works. Let's see. Oh, okay. Yeah, see that? It's not equal there. Okay, so now I'm going to do the next one. Y equals k, and the domain x equals 5. Add a slider. Now this one's hard to see. Okay? It's hard to see. All right. So let's see if we can find it. What if I do this? 4.9, 5.1. So I can try to see where it is. So right around, okay, so this increment's not going to work. So let's see if we can't, 0.7. Oh, there it is. Now it's continuous. So you might have to like fiddle around a little bit to make sure that it actually works. There it is. I could probably even try to 99, 5.01. Make sure it's actually a single point, because it's not going to graph holes. You're going to have to work your way into finding it. Okay. Your job is to solve 7 and 9 and check them graphically. If you finish those two things,